This video is going to cover epidemic curves, which are a way of showing basically just how the number of cases are changing over time, which can tell us a lot about an epidemic. And it's something you might have heard of just through people talking about COVID, talking about flattening the curve. They're generally talking about this. So this is basically what an epidemic curve looks like, where the y-axis is the number of cases, and the x-axis is the number of days, or I guess like a carefully chosen time interval. And I'm going to get into how the time interval is chosen, just because based on the time interval you choose, you might get a very uninformative graph, or you might get one that is able to really show different features of the outbreak. So what I mean by that is some features of the curve are here we have like the lead up time. Ideally, there should be some time before the outbreak begins, shown on the graph to show that it's an epidemic. It's coming out of nowhere, kind of. There's a peak. You see it ramping up here, and it comes to a peak, and that has features that we can use to, I guess, find information. And that's something I'm going to come to in a bit. And finally, there's this lead out period, I guess, and that should always be shown on the graph just to demonstrate that the epidemic has come to an end. So, depending on the shape of the epidemic curve, you can have some information about basically what type of epidemic it might be, what type of source might be causing the epidemic. So you can you can see this one here is really like kind of uniform, almost like a rectangular distribution of cases kind of steadily coming out. And you can imagine what kind of source of infection that might be. You can see that new cases are kind of coming at a steady rate. So basically that means that this needs to be some kind of steady, ongoing source of infection that we would call a common source. And that's different than this other example, which is a point source. So that's easier to understand when you contrast it to this, where you can see that there's a spike. Basically, we can almost assume that any of this variability is biological. It has to do with how basically rapidly the person's immune response changed. We can basically assume that everyone here was infected from the exact same source, an event that happened at like an instance in time, and this variability is mostly a product of just how fast the infection takes hold in an individual. Well, here we have this we're not able to really differentiate a peak necessarily, so that tells us that there's probably some ongoing source of infection, like a water source in that classic like cholera epidemic. If this just is just an ongoing source of infection from the Broad Street pump, say, we're not going to really see like a peak necessarily. We might kind of see a distribution more like this, where people are getting infection on a daily basis, different people. So there's not really a peak necessarily. Something neat about point source outbreaks, like I said, there is a specific instance in time that it all began. If you know a bit about the disease, like the incubation period, that's the time between becoming infected and developing symptoms. So if you know that that's like, say, an average of 4 days, you can count back 4 days from the peak, and that can give you an estimate of when this point source of the outbreak might have been. Just because that's kind of based on this assumption that the peak is going to, like, the average incubation period is when we're going to see the most people develop symptoms. And again, there's going to be some biological variability, but if we count back 4 days, we can assume that on this day, basically there was some big source of infection that took another 4 days for most people to develop symptoms. While they were infected all of this time, they only became symptomatic here. And we can get kind of like what's equivalent to like a confidence interval around this if we do the same thing from like the last observed cases. If we go 4 days back from that, and the first observed cases 4 days back from that, we have this like kind of confidence interval around where we think the outbreak might have began. The last thing is a propagated outbreak, and that's here we can just see that it's kind of coming in waves. And what we can imagine happened here is there might be, it could be some source from the environment, but maybe we just have an outbreak at like some party or something, and then we have people who become infected there going out into the world and infecting other people, and becoming the source of outbreaks in other locations. Basically, is what gives rise to a figure like this. So now just going through an example of how an epidemic curve would be constructed. You typically have data like this. This is what you would be presented. Like an example you sometimes see is like an outbreak on like a cruise ship or following a dinner or something. But yeah, you might not even know what the disease is, but you generally have like the time of onset of symptoms, and each of these represents a different person. And then you need to think about how you're going to group the time. Um, so what people often choose is some fraction of the incubation time. So like half or a quarter of the incubation time. So let's just say the disease that we're looking at. I'm not even gonna like make up what the name is or what disease it is. Let's just say it's like a 24-hour incubation period. So we're going to choose like 12-hour intervals. And what this would look like is these people on like the first case was on January 5th at 7 p.m. So if we break it into intervals that are like what I went on to do here is like on each day 12 p.m. to 11:59 p.m. And then just that and these intervals in between would, for example, would be like it would begin here at 12 a.m. on the 6th and go all the way to basically 11:59 a.m. on the 6th. Yeah, so basically we can separate these into these 24-hour intervals, where two people fall in this first interval of like 12 p.m. to 11:59 p.m. on the 5th. And we can keep doing that for each of these intervals that we established. We have four people that are between 11:59 p.m. on the 5th and or so, yeah, 12 a.m. on the 5th. So we have 1 a.m. on the 5th, and the last one here is at 11 a.m. on the 5th, and that new interval would start at 12 p.m. So basically, we have one, two, three, four people in this interval. Sorry, this is an awkward one to explain, but basically, if you just look here on the x-axis, we have it's separated into 12-hour intervals, and the 59 makes it look kind of weird just because you can't have the next interval overlap with the other one. But yeah, if you just kind of trust me that they're separated into 12-hour intervals, and the one that's not written here is just the kind of implied 12 hours in between. And if we just keep doing that, we see the most happened here, and I'm just reorganizing or restructuring the table so it all fits here, but it's basically just taking parts of this table out. And yeah, we just keep doing that until we've plotted basically all cases in the outbreak divided into 12-hour intervals. Then we can start trying to figure out when this outbreak might have began. Again, we have this 24-hour incubation period, which is an average. So to get like our point estimate of when we think it began, we go 24 hours from the peak. So 12 hours, 24 hours, and to get this like confidence interval around it, we go 24 hours back from the first interval with cases, and 24 hours back from the last interval. And yeah, this is just an example I kind of made up. This obviously like this confidence interval like it covers like a big part of the epidemic, so this one isn't that informative, but it's just one I created just to show you how you would go from data to an epidemic curve.